We are Group 33, and our project is the Motion Detecting Sentry Turret. Our group consists of one electrical engineer, Caitlin Martin, and three computer engineers, Ladar McGarry, Michael McAllister, and myself, Quinton Jimenez. The overlap in our majors has allowed the team to work more seamlessly together on different aspects of the project. The key specifications for the Motion Detecting Sentry Turret are outlined in this table. Among the primary specifications, the sentry turret must be accurate to a minimum of 70%, meaning that 70% of shots fired must hit their mark. The turret must be able to traverse or rotate 180 degrees horizontally and 45 degrees vertically. The range of effect for the turret is required to be between 10 and 75 feet from the device itself, within the cone defined by the horizontal traversal specification. The power supply should last 3 hours on a single charge. The minimum ammunition capacity should be 20 rounds, and the maximum weight of the device should be 40 pounds.
Here we have Group 33's computer vision paintball turret. The main change from Senior Design 1 is the base. This is due to choosing to use reclaimed material in order to remain within budget. Otherwise, here we have the chassis that holds the Y-direction stepper motor with a shaft connected to the gun, which is held on to the shaft with a shaft clamp and bent a piece of metal which cradles the gun and is then clamped using hose clamps. On the base, we have a plate that holds the Y-direction stepper motor connected to another shaft, which is then connected to the whole chassis. Under the stand, we have our batteries and air tank, which also serves to weigh down the system in order to have it not move during a game. Moving on to the electrical box, we initially chose to use solid core wire, which is very stiff and difficult to route and organize. Within the box, we have two stepper motors and our PCB. This PCB serves as the hub between the computer vision running on the laptop, and then to the drivers, and then to the stepper motors and trigger servo. Going back to the PCB, there are 4 limit switches, which allow us to calibrate the camera and stop the system from going out of bounds and breaking the setup. Ideally, we have a larger electrical box for wire management and to properly mount our PCB within. At the very end, we also taped on a laser pointer onto the shaft of the gun. This allowed us to test without needing to get hit by a paintball gun every time. It also allowed for better accuracy when calibrating and finding out where the gun was pointing in order to troubleshoot and better understand what was happening.
As for the software libraries we'll be using, our programming will be split between Python for computer vision and Arduino C on the microcontroller. For computer vision, we'll be using OpenCV and its built-in Hog plus SVM pedestrian detector. MUtils and NumPy are utility libraries that allow us to manipulate images and arrays. The keyboard library will allow the program to take raw input directly from the keyboard without requiring the user to press the enter button, which is useful for the turret's manual control mode. PySerial allows serial communication with the microcontroller. In the Arduino code, we're using the servo and stepper libraries, which simplify the control of said motors. And SPI, or the Serial Peripheral Interface, allows us to communicate with the Arduino through a serial connection. In our senior design paper, we specified that the turret's range should be between 10 to 75 feet. Our completed turret has an effective range of 10 to 30 feet. The turret is capable of detecting targets past 30 feet, but with terrible accuracy. And the turret is incapable of detecting targets at all past 40 feet. The turret always prioritizes the target closest to its current aiming position and moves towards them. When a second target is detected, it will be ignored unless it is closer to the turret's crosshairs. When 2 targets overlap, the turret defaults to the first detected target. The target detection algorithm is imperfect, and there will be frames when a target is undetected. This is usually not enough to disturb target prioritization. However, this means that moving targets, which are detected less consistently, tend to be prioritized below stationary targets. While we tested target prioritization with 2 people, our algorithm can theoretically work with an infinite number of targets. In the bottom right of the screen, you can see the prioritized target's position and the turret's current position in X and Y coordinates. Notice that it continues to target me in the center over Katie at the edge, even when she walks in front of me.
Here we have the turret following Michael to line up a shot. Since we are indoors, an alternative laser pointer is used as a firing device. As you can see, the resulting shot lines up with the upper torso and counts as a successful try. Here is another clip of our accuracy testing. As you can see, the results were reproduced with our laser pointer. Here we have the traversal of the turret. As you can see, it goes horizontally 180 degrees and vertically 45 degrees. From this view, you can see the gears moving left to right for horizontal movement. It is restricted from moving off the 180 degrees by limit switches. This view shows the vertical view of gears moving 45 degrees up and down, stopped by the limit switches. Here we can see an entire horizontal traversal, tracking a person from the entire view of one side of the camera to the next. You can see the warning light come on as a person is detected, and it goes off as the person leaves. Also, you can see our alternative firing method as a laser pointer is shown. Here is our actual results of the testing. Our accuracy landed at 50% due to overcompensating targeting and lack of frames. Our traversal was a success, and our range was 10 to 30 feet, which landed into our effective shooting range, which was successful.
During the course of development for the motion detecting sentry turret, the members of Group 33 compiled a list of improvements that they would like to see should the project be reproduced. First, the group believes a larger electrical box would be beneficial toward more discrete cable management. Currently, the electrical box used does not effectively contain all cables. Next, the group would elect to use a different servo for the triggering mechanism than the Tower Pro MG995. This is because multiple Tower Pro MG995 servo motors broke or malfunctioned throughout the project. Through troubleshooting, the group determined this was caused by one of 2 issues. Either a particular gear within each tested servo broke in operation, or the potentiometer within the servo malfunctioned and failed to stop as the motor rotated toward 180 degrees, causing the motor to rotate indefinitely. Another improvement which should be made is the GPU used to process computer vision algorithms. In our project, the machines used defaulted to CPU usage over GPU because the available GPUs were unable to perform the necessary calculations. As a result, the frame rate suffered significantly on multiple machines, reaching as low as 2 frames per second. The batteries used for the sentry turret were much loftier than desired and increased the total weight of the device past the expected limit. Also, using rechargeable batteries would add to the longevity of the device. Finally, any group with the intention of reproducing this project should ensure a large enough budget to improve the aspects of hardware listed above. A large portion, roughly 20%, of our current budget has been used to replace damaged or malfunctioning parts.
This was Group 33's final demo. Thank you for watching, and have a great day.